And now we're going to continue in with Chapter 3 with this second lecture. And here we're going to look at the Kelvin temperature scale, as well as the more familiar Fahrenheit and Celsius temperature scales. Now, before we do that, we need to understand what temperature is. Now, in physics, we talk about energy a lot, and there's lots of different kinds of energy. There's nuclear energy and chemical energy and thermal energy, the energy of heat that we're going to be talking about here. But another kind of energy that's very important is called kinetic energy. And kinetic energy is the energy of motion. That is, it takes energy in order to make something move, and the energy that that object has by virtue of its motion is called its kinetic energy. So I have my definition written out here. Kinetic energy is the energy of motion. And so if anything is moving, it has kinetic energy. And the formula, there's a physics formula for calculating kinetic energy, and it's simply this. The kinetic energy of a mass is equal to 1/2 times the mass times the speed it's going squared. So you take the speed, you square it, multiply it by the mass, and you divide that whole thing by 2 or multiply by 1/2, and that gives you the kinetic energy of that moving mass. And so anything that is moving has kinetic energy. Now, let's think about you. You may be sitting in a chair watching this video, so you may not feel like you're moving very much. But if you zoomed in with like a super duper microscope and you could actually see the individual atoms that make up your body, you'd see they're vibrating back and forth really fast. And so the atoms and the molecules that make up your body are moving through this vibration. And so therefore, the atoms and molecules of your body have kinetic energy. Now, temperature is the measure of the average kinetic energy of all the atoms and molecules of your body. So I've written it out here. Temperature, this is the definition of temperature. It's the average kinetic energy of the atoms or molecules of a body. So your body has atoms and molecules that are vibrating back and forth, and if your temperature is increased, if you go from a freezer into a sauna, what's going to happen is the atoms and the molecules of your body are going to be vibrating faster, because what you can see is that a bigger speed represents a bigger kinetic energy. And so that's what temperature tells you. It tells you how fast the atoms and molecules of your body are vibrating back and forth. Now, how do we measure temperature? You need something called a thermometer. A thermometer is a scale that relates a physically changing parameter to a change in temperature. Now that sounds fancy, but it really is a simple idea. So let's take an old-timey thermometer. This is the kind that everybody's familiar with. It's a glass tube, and the really old-timey ones had mercury in them, but mercury's pretty toxic, so now they put alcohol with a little bit of food coloring in them. And so you have this sort of reservoir at the bottom. I'll pick this one. You've got this reservoir at the bottom, and you have this hollow glass tube, and as the temperature of the thermometer increases, the stuff inside expands. Now, actually, the glass expands a little bit too, but the stuff inside expands more. And so as the temperature goes up, it'll expand up the inside of this glass tube and go higher and higher. And then they just mark different levels, and they assign degree values to them. Now, the most common scale in the United States is the Fahrenheit scale. The Fahrenheit scale is based on the boiling point and the freezing point of water. And so what they do is they take a sample of water and they cool it down until it freezes. And wherever the level of the thermometer is when the water freezes, they mark it there and they put a 32 there. And then they heat the water up until it boils. And when it just starts to boil, they put a 212. That means there's 180 divisions between the freezing point of water and the boiling point of water, and that's how they define the Fahrenheit scale. And of course, it's possible to get colder than the freezing point of water, and it's possible to get higher than the boiling point of water, but that's how the thermometer is built when using the Fahrenheit scale. Now, for the Celsius scale, they do the same thing, but instead of calling this 32, they call it 0, and instead of calling the boiling point of water 100, they call it 100 degrees. And so now there are 100 divisions between the freezing point and the boiling point of water. And so it's kind of like you measuring a distance in miles or measuring a distance in kilometers. It's just, you have a different way of dividing up the distance. Well, the temperature degrees are just a different way of dividing up the distance that this alcohol has moved up the thermometer between these two temperatures that are our reference temperatures. Now, there is a special form of the Celsius thermometer that was developed by a guy named Kelvin, and so we call that the Kelvin scale for the thermometer. And the Kelvin scale for the thermometer is based on absolute zero. It's not based on the freezing point and the boiling point of water. But what they said is, okay, in the Celsius scale, there's a certain distance between each of these degrees because I divided them into 100 between here and there. What I'm going to do is I'm going to get the coldest temperature you could possibly have in the whole universe and call that 0, and then I'll just add Celsius degrees. And when you do that, you find that water freezes at 273 degrees on the Celsius scale, and it boils at 373. Again, there's a 100-degree difference between the freezing point and the boiling point of water, but the bottom of the scale is 0. And for this reason, it's called an absolute scale of temperature. And so this 0 is called not just 0, like up here we've got 0, there'd be a 0 down here on the Fahrenheit scale below the 32, but those aren't absolute zeros because it's still possible to go lower temperature. You could have negative temperatures below the 0. But on the Kelvin scale, you can't go any lower than that. That's the lowest possible temperature. Now, how does that happen? How do you make the lowest possible temperature? Remember what temperature is. It's the average kinetic energy of all the atoms and molecules vibrating back and forth. So if I think about the kinetic energy of an atom that's vibrating back and forth in my body, as the velocity or the speed gets smaller and smaller, the kinetic energy is going to get lower and the temperature is going to get lower. But what's the slowest speed that my atoms and molecules could possibly get? 0. You can't go any slower than 0. So once your atoms and molecules seize up and they stop vibrating altogether, you can't get any colder than that. That's as cold as you can possibly get. And that's called absolute zero. Now, just for completeness, I want to mention one thing. I've talked about atoms and molecules vibrating back and forth, and that makes sense if you're talking about a solid or a liquid. If you have a gas, then you have a bunch of atoms and molecules just bouncing around inside the room or inside the container. And again, what it means when you increase the temperature, the velocity or the speed increases, and they're just bouncing around faster. And so that is how it applies to a gas as well. But these are the 3 temperature scales, and that is how they are used. The next topic that I want to talk about is something called blackbody radiation, or the blackbody spectrum. Now, when you think of something emitting light, and this could be visible light, it could be infrared light, it could be ultraviolet light, whatever it is, if something is emitting electromagnetic radiation, if that object is a blackbody, then that object is going to be emitting all the possible frequencies or all the possible colors over a range. And so what you can see here in this PowerPoint slide is a typical graph of a blackbody spectrum. And on this graph, you can see there's the intensity axis, and so that would be the brightness of the light. And then you can see the frequency axis. And sometimes you'll see it with wavelength instead of frequency. Both are very common, and of course, we already talked about in a previous video that frequency and wavelength are kind of related to one another. But over the range, so from the frequency here, this thing is emitting light, and it's emitting more light, brighter as the frequencies get higher. But then there's a frequency. This frequency down here corresponds to the brightest light emitted by this object. And then at higher frequencies, it starts to emit less and less radiation until you get to a point where no more light is being emitted of these frequencies. But every frequency in this range, from here to there, there's some brightness of light that's being emitted. And so that's a blackbody. Now, one of the things that's important is this idea here, that when you have a blackbody spectrum like this, the radiation emitted by an object, it depends only on its temperature. And so it's the temperature of the object that's causing it to emit its spectrum. Now, how does that work? Well, we're going to put together some of the previous ideas that we've talked about in these 2 lectures. First of all, we know that anytime you have charges that are vibrating back and forth, that's going to generate electromagnetic radiation. And so you have atoms and molecules that are made up of protons, neutrons, and electrons. And those protons and electrons have charges. So as the atoms and molecules of your body vibrate back and forth, guess what you're emitting? You're emitting electromagnetic radiation. And here's our key idea. Anything that has temperature is also emitting electromagnetic radiation. Now, most of you are sitting in a room that's probably at a temperature of about 300 Kelvin. And by the way, you don't say degrees Kelvin, you just say 300 Kelvin. So you're sitting in a room that's probably around 300 Kelvin, and guess what? That means that your temperature is around 300 Kelvin. And things that are around 300 Kelvin, they emit radiation in the infrared. And so you are giving off electromagnetic radiation in the infrared part of the spectrum. Now, human beings can't see that. We can only see the visible part of the spectrum, but you're still giving off radiation even if you can't see it. I like to talk about, some of you may have seen some of those Predator movies where the predators are hunting the humans. They're these aliens. And in this science fiction film franchise, the predators, they don't see visible light like we do. They see infrared. So if you're hiding in the forest, they can actually see the temperature that you're giving off, and it sets you apart in the bushes. Now, if you were heated up to about 6,000 Kelvin, that's the temperature of our sun, more or less, at the surface of the sun, you would be giving off visible light. And we kind of see this sometimes if you think about it. Now remember, the lower frequency parts of the visible light would be the reds and the oranges, and then as you get up more and more, you go to the part of the spectrum that has the blues. If you take an iron poker, like from a fireplace, and you put it in the fire and you heat it up so that it's glowing, as it heats up, it doesn't glow right away, but eventually it starts glowing red and orange, because as you're heating up, those atoms and molecules are vibrating back and forth faster and faster. And if they're fast enough to give off visible light, they're going to start giving the red light. But as you add more and more temperature, more and more atoms are going to be vibrating faster and faster. You start to add in all the other colors. And that's why if you heat something hot enough, it becomes white hot, because it's giving off all the colors. And you probably learned again in grade school that something that's giving off all the colors, if you have all the colors combined, it makes white light. And so that's why something can be literally white hot, because it's giving off all the colors. Now here we see a graph that's got a few different blackbody spectrum curves, and you can see there's one for 300 Kelvin, and here you see this rainbow. These are the frequencies where you would be emitting visible light. And so you can see that if something is at 300 Kelvin, it's not emitting any frequencies that would be visible light. This would be just emitting infrared. Now if you heat it up hotter so that it's 1,000 Kelvin, you can see that some of those oranges and yellows are being emitted, and so that's why that hot poker starts to look orangish and reddish. But as you heat it up more, say to 5,000, you get more colors emitted, and even some ultraviolet that we can't see. And as you increase to 7,000 Kelvin, you can see that the peak is actually over here in the ultraviolet, but you're still going to get a lot of the visible colors too. And for our sun, the temperature would be peaking right in that yellow here at about 6,000 K. That's not drawn on this graph, but that's where it would be. And so the different temperature blackbody curves show you the different frequency ranges that each of those different objects at those different temperatures, the light that they would give off. Now, here is the next thing in the slide we want to talk about, we want to look at these radiation laws. And the first radiation law that we're going to talk about is the peak wavelength is inversely proportional to the temperature. And of course, that means the frequency is directly proportional to the temperature. But what that means, what does that mean, the peak wavelength? That means the wavelength, and we can see the wavelengths down here, or the frequency that corresponds to the brightest light emitted by the blackbody. So here we can see it's getting brighter, 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 brighter. Here it's brightest, and then if you keep going, it gets less bright, and then it's not emitting any more color. So here would be the peak of this curve. There would be the peak of that curve, the peak here, the peak there. That's where it's the brightest light, the highest intensity light that it's giving off. And so you find that frequency or you find that wavelength, and that would be the peak frequency or the peak wavelength. And so we'll see a formula in a minute how you can use this to calculate it, but that is the relationship, and that's what it's meant by peak wavelength or peak frequency. Now, the next radiation law, it tells us that the total energy emitted by the blackbody, and again, these are all talking about blackbodies, the total energy is proportional to the fourth power of the temperature. And so we can say that the energy is proportional to the fourth power of the temperature. In other words, if I've got something that's radiating electromagnetic radiation, it's giving off energy in that radiation. Now, if I double the temperature, if I heat it up twice as hot, I'm going to have 2 to the fourth power times as much energy. And of course, 2 to the 4 means 2 times 2 times 2 times 2, and that gives us 16. So doubling the temperature means you get 16 times as much energy emitted by the body. Now, that first slide said that the peak wavelength is inversely proportional to the temperature. You can turn in proportionality into an equation by multiplying by a constant, and it turns out that this is the right constant to use. And so the formula that we have is called Wien's law. Now, it's kind of weird because it's Wien's law spelled with a W. Wien was a German guy, and in German, the W's are pronounced like English V's. So this is actually called Wien's law, and it tells us that for a black body, and I'll just make a note, that's for a black body, the peak wavelength, and that's what this lambda max is, that's the peak wavelength. And we just talked about in the maximum slide how to find that from the blackbody curve. So the peak wavelength is equal to 2.9 millimeters divided by the temperature. And so what does that tell you? Why am I bothering showing you this? This is one of the coolest things that we'll talk about in this course. This is so freaking cool because what this means is that if I look at, say, a star from billions and billions and billions of miles away, if I plot out the brightness of the light for every color, in other words, I plot the blackbody curve for that star, and then I find the wavelength of the light that is the peak wavelength, I can calculate the temperature of the star. It wouldn't be possible for me to travel to some distant star and put a thermometer in that star and measure its temperature. But what I can do is I can look at the light being emitted by that star and find out, okay, at this color it's a little bit brighter, at that color it's a little bit less bright, and I can find the color. And remember, that color might be in the infrared, it might be in the ultraviolet part of the spectrum, it might be somewhere in the visible, but somewhere is the maximum energy coming out of that star. And if I find the color, the wavelength of the color can be plugged into this formula, and I can solve for T, and that will tell me the temperature of that star, no matter how far away it is. That's pretty darn cool. Now, the other radiation law that we talked about was we said that the energy emitted by a black body was proportional to the temperature to the fourth power. And this is actually an example of what's called Stefan's law. And we can see the formula for Stefan's law right here. So we have this term F, and it says energy. Actually, it should be power here. A power is energy per time. So that's power. Not energy, but power. So the power radiated per unit area is proportional to temperature to the fourth power. And to turn a proportionality into an equation, you multiply by a constant. This constant is called Stefan's constant. And so if F is power per unit area and it's measured in watts divided by meters squared, and if temperature is measured in Kelvin, then the constant sigma would be 5.67 times 10 to the negative 8 watts per meter squared Kelvin squared. And this negative 8 should be an exponent there. In any case, we have the relationship for Stefan's law that the power per unit area is proportional to the fourth power of the temperature. Now, the next thing that I want to talk about is the Doppler effect. And basically, this is very important to understand for astronomy, because if something is giving off light, we want to measure its wavelength or its frequency. But if the thing that's emitting light is moving towards us, we'll measure a different frequency from it than if it were standing still. Now, this is important for us for two reasons. We need to be sure about which frequency we're measuring, the frequency of a stationary thing or the frequency of a moving thing. And if the frequency is changed from what it should be for something standing still, we can also tell how fast the thing is moving. So again, this is really cool. By looking at the light coming, say, from some distant star, we've already talked about how we can use that light to calculate the temperature of the star. Now we can measure how fast it's going and which direction it's going based on the frequency shifts in the light that it's giving off. Now imagine there's you and there's something emitting a wave. If you are traveling towards the thing or the thing is traveling towards you, the waves that it emits will appear at a higher frequency than if the thing were standing still. Now, if you on the thing giving off a wave are moving away from one another, either you're standing still and the wave source is moving away, or the wave source is standing still and you're moving away, the wavelengths will seem to be at a lower frequency than if everything was standing still. And I'm actually going to put up a separate YouTube video into our module so that you can see how this works directly. Now, in this slide, we have a formula where we can say the ratio of the apparent wavelength, that's the wavelength that we measure, versus the true wavelength, that would be the wavelength the thing had if it were standing still, is equal to the true frequency over the apparent frequency, which is also equal to 1 plus the speed with which the thing is moving divided by the speed of the wave that's being emitted. Now, the good news is I don't expect you to memorize or know, or even I'm not even going to ask you to use this formula, but I put it in this presentation because what I want you to understand is that there is a formula. There's a mathematical formula that if you know how much the wavelength of the light has changed, you can tell how fast the object that gave off that wavelength is moving. So again, I've got a star that's emitting light. And if I look at the wavelengths of light being emitted by that star, if they're a little bit more red than the wavelength should be, I know that star is moving away from me at a low speed. If it's really a lot more red than it should be, I know that star is moving away from me at a very fast speed. Now, if the star is moving towards me, it's going to look more blue because blue would be a higher frequency light. And remember, if the thing is moving towards you or if you're moving towards it, the wave seems to have a higher frequency than it really does. So here we have the last slide, and I'm going to try to explain using this slide how the waves kind of bunch up and create the appearance of a higher frequency or lower frequency. But this is actually difficult to understand from a static picture, so that's why I'm going to put up a separate video with an animation that really shows how this works. So let's take a look at this. In the figure here up at the top, we have something that is giving off, let's say, electromagnetic radiation, and these represent the waves. And so it's the outermost one was the first wave pulse that was sent out, then the second, the third, the fourth. Each of these rings represents the crest of the wave. And so there's a certain frequency that would be measured. So somebody over here that's measuring their receiver, they get the first pulse, and then a little bit later they get the second pulse, then the third and the fourth, bop, 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 bop. They could count how many bops there were per second, and then they could tell you what the frequency of that wave would be. Someone over on the other side would measure exactly the same wave because everything is stationary. Now, what happens when the wave starts to move? When the object is in position 1, it emits the first pulse. But now it's moving to the right. So when it emits the second pulse, instead of being in position 1, it's moved over to position 2. And so the wave from position 2 starts a little bit further over to the right than the first pulse did. And then by the time the third pulse is emitted, the object is at position 3, and the wave is shifted over to the right even further. And so what happens is on the right side, the waves are bunching up. And so someone over here would feel these hitting a lot faster. Instead of bop, 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 you get bop, 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 bop. And so it'd be a higher frequency. Now someone over here, the waves are bunching up over on this side. It means they must be spreading out on the other side. And so someone over here, where the source is moving away from them, the waves are spreading out, so they would measure bop, 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 bop. They would get fewer bops, and they would measure a lower frequency. And so here, the light would be given off. Someone on this side, the way towards the direction of motion, they would perceive the light as being more blue than they would if it was just standing still. And someone on the opposite side, the motion is going away from them, they would perceive the light as being more red shifted than it would be if it were standing still. Now, this can work with any kind of wave, by the way. It can work with sound waves or light waves or any kind of waves. And in the video that I'm going to put up, it's actually going to use sound waves to kind of describe this phenomenon, because I think you'll see that that actually makes it a little bit easier to understand, because it's something that you'll have had practice with in the real world, or experience with, rather, in the real world. So anyway, look for that video, and that constitutes the last of the material that I wanted to review for Chapter 3.